Hello. In this video, we're going to go over some of the CAD simulations for the multistage amplifier. At this point, you should have made a theoretical analysis and have a good foundation of what the values are, and have made a schematic on LTspice. If you have not made your schematic on LTspice, I suggest pausing this video and making your schematic before continuing to do the simulations. So the CAD simulations we're going to go over today are the DC analysis, the transient analysis, and the AC analysis. So I'm going to pull up my schematic, and if you press this .op button, or the shortcut is S, it'll give you the directives, and you could press .op and then move wherever you want, and then on the mouse, the left button, just drop it, and then you would run it, and it would give you all of these values as your DC operating points. So the problem is, you notice how it says node 2, node 7, node 9. It's kind of hard to tell what is what on here. So one thing we can do is just move the mouse to like the base, and then left click on the mouse, and it'll give you the voltages. Right, so the base, collector, emitter. Another thing we could do is right click on the mouse, go to draft, go to net label, and the shortcut is F4. And we could do voltage at the base stage 1. And this is what I would suggest to do for every single DC operating point. And I'm just going to do a few of them to show you what it looks like. So after putting this first stage transistor in, you would run it, and it gives you VC1, VB1, and VE1. So the first thing that pops out to me is VC is 13.58 volts. That's very high, and to me it looks like it's going into cutoff mode. And then I look at the voltage at the base, and it's 0.8. Okay, so I got a 10 meg R1, 620K R2, and I go to my theoretical that I did on my Excel sheet, and the voltage at the base is just a voltage divider, and I'm getting 1.167 volts. And so if we're getting 0.8, a little over 0.8, and then we have to do a 0.7 volts drop through the diode, we're going to have a lower voltage through the emitter. And if we have a lower voltage through the emitter, then using Ohm's law, the voltage through the emitter divided by the resistance of the emitter, for me it's RE1 and RE2 because I'm using the swapping resistor, then the current's going to be even lower. So, you know, my current, I'm using 668 microamps, and I go back and look at this, and I go down to the emitter for the Q1, and I'm getting 267 microamps, which is significantly lower. So you can see that just a tiny change through the voltage at the base makes quite a big difference, whether it's going into cutoff mode or saturation or staying in the quiescent point. So, you know, looking at my voltage through the collector for the theoretical, I'm around 4 volts. And so if I look at the AC and DC load lines, so AC load lines here, DC load line is there, and this is my quiescent point. And if I drag it all the way down, this is about 4, which is our 4 volts for VC. And then this point, if we drag it to the left, that's about, 0.00065, I would assume, if I didn't know that it was actually, 668 microamps. So that was just a point I wanted to make, that there's going to be difference between your theoretical results, your simulated results, and eventually your experimental results, and that's okay. I would recommend going through here and making sure all of the values are exactly what you calculated for your theoretical, and make sure eventually with your experimental that you're using the right values. And just observe, just like how I did. I noticed, hey, my VC1 is really high. Why is this transistor going into cutoff? Oh, it's because VB1 is a little lower than expected. Or if there's a lot of current going through here, maybe, VB was higher than expected. So just make observations and document them in your lab document, your lab presentation. So that's operation, DC operating points, your DC analysis, and yeah, you just take this, take a snip of it, put it in your lab, and observe the Q point, VC and IE. Okay, moving on to the transient analysis. So the transient analysis, you can go to simulate and go down to edit simulation. There's a transient analysis graphical user interface for quite a few common used directives, excuse me. So let's make this stop time 10 milliseconds, and let's make the start time 0. So if your graph ends up looking black like this, I recommend that you change it to white, because it's going to look a lot better on lab presentations, and in the future when you're doing IEEE reports, if you take a snip of your result, it's going to look a lot better on those type of reports. So we can do that by going to Tools, Control Panel, Waveforms, Color Scheme, and then selected item, go down to Background, and then use the RGB sliders to turn it white. And then we're going to have to go to Grid and turn the grid black. And then apply and hit OK. Okay, so now we're going to measure the input. So the input, I'm using 10 millivolts peak, and I wanted to point out in the lab, it says for transient analysis, use a VN of 1 millivolt. And I recommend using 10 millivolt peak, because when you get to the experimental results, if you go to the lab, the function generator only goes to 20 millivolts peak to peak. So at this point, I would recommend doing 10 millivolts peak or 20 millivolts peak to peak, however you like to describe it. Okay, so we're doing 20 millivolts peak to peak, and our output looks a little less. Oh, and I see the reason why. my theoretical analysis, I used a series resistor of 8 kiloohms, and I had a different value in there. So let's look at it again. There we go. Okay. So one thing I wanted to point out is, since we're taking the transient analysis and the time to start saving data is 0, sometimes on certain circuits it takes a minute, takes an amount of time for the signal to stabilize. And you can see that right here. This bottom portion of the sinusoid is below negative 1.2 volts, where the 10th cycle is above negative 1.2 volts. So we can work around that by changing the time to start saving data. Let's give it a little bit of time, like 100 milliseconds, and then we could change the stop time to 110 milliseconds. So now we run it, and they're all above negative 1.2 volts, and they're not really changing much. Okay, so I had a professor tell me a long time ago that if you're taking screenshots of sinusoids for a report, it is good to have like 2 or 3 cycles. We don't need 10. So to get 3 cycles, we could do 103, right? Because the stop time's 103 milliseconds, and we're starting to save data at 100 milliseconds, so that gives us 3 milliseconds. And there's 3 cycles, and that's because we're using a 100 kilohertz signal, right? And the inverse of 100 kilohertz is 1 milliseconds. So I'm just taking 1 milliseconds, and I know that 3 milliseconds is 3 cycles for that specific frequency. Okay, so if we wanted to measure this, you'd come up here and right-click. You could change the color, and I'm going to use 2 cursors to measure the output, and then we get this kind of data chart, and we're going to look at the difference. We're looking at this value. So for the first cursor, what you got to do is you hover your mouse over until it turns into a 1, and then you use the left button on your mouse and you can drag it. So put that at the lowest point, and then put the second cursor at the highest point, and then that's our output. Our peak to peak output is 2.28 volts, peak to peak. So if we look at our input again, which was 20 millivolts peak to peak, and our output was, what was it, approximately 2.3 volts peak to peak, we're over 100 gain. So what you could do, if you're getting a little more, is just take your series resistor and increase it to attenuate the signal a little bit. Right, so I just increased it from 8 kilohertz to 50 kilohertz, and now I'm below 100. So you could play with it and find that sweet spot, and just make sure to incorporate it into your calculations and your theoretical if you do end up going that route. Okay, so that's the transient analysis. You could end up making this bigger, putting your graph in a nice place, and take a screenshot of this for your report. Okay, to do the AC analysis, so what I did there is I just right-clicked on the directive and it'll pop up this screen. Or if you want, you could go to simulate. I guess you can't. This has to be gone. If that's gone, you can go to simulate and go to edit simulation. So we're going to do an AC analysis, and the type of sweep, we're going to do a decade. The number of points, I'm going to go with 100, 100,000. Start frequency is going to be 1 hertz, and the stop frequency, I'm going to go with 2 megs. And wow, I messed that one up. 2 megs. And make sure it's capital M, lowercase e, lowercase g, otherwise it won't work. And then you press OK, bring your directive down wherever you want it, and then run it. And then we're going to right click to get our cursor. We're just going to use one cursor because the frequency response for the lab is only the lower cutoff frequency. And to look at the lab, let's see. Lower cutoff frequency needs to be less than or equal to 100 hertz. Okay. I'm going to change this back to 8Ks. So we're looking at the passband. This is the first thing that I do, look at the passband. In like the middle of the passband, what's the magnitude? So it's 1.23 dBs. And the lower cutoff point is going to be 3 dBs down. So that's going to be negative 1.77 dBs. So what I'm going to do is move this cursor down until I get the magnitude to negative 1.77 dBs. So I'm pretty close, and then I can use my arrows on my keyboard to get it like really, really close. Sometimes it's hard to do with the mouse. Okay, so my lower cutoff frequency point is 58.9 hertz. So your circuit, might not be 1.23 dBs in the passband. If we change this to 50K like we had it before, it's negative 270 milladecibels, so that's pretty close to 0.3. So what we would do is we would subtract it by 3 dBs, and we'd find that spot to the left. So if this is approximately 3, then we're going to take it down till it's at negative 2.7. Which is about 68 hertz. So I just wanted to point out that your amplifier, the passband magnitude might be different. Oh, I'm sorry, it was negative 270. So if it was negative 270, we would want to go down 3 dBs, so it would be negative 3.27 dBs. Negative 3.27. And that makes sense because 58.7 hertz, that's what we got when it was at 8 kilohertz. And then if you want to change the frequency response, I suggest first off, I suggest watching the workbook activity videos on Canvas, and also, experimenting with some of these capacitors. Like, you have your coupling capacitors, which allow the signal to go through without being affected by DC, and we have these bypass capacitors, which also allow for a lot of gain. So if you were to just change a couple capacitors or one capacitor, that's a low pass capacitor, you'll see that it affects it quite a bit. And typically there's going to be one dominant capacitor. And again, if you go through the workbook activities, there's a section on calculating the frequency response. Thank you.